Oh, sorry. Do you hear me now?
Yes.
You're welcome to record. Do you see the slides now?
Yes.
Perfect.
Then you're welcome to go ahead.
Thank you. Okay, so I'll be introducing work that I did in collaboration with Ahmed Salim Al-Zabi, Christoph Lai, who just gave us a nice talk on skewed by variable mimesis, and then Thomas Hammelwork. And this is an implementation of recent developments in Stein variational inference into a framework called NumPyro. And so we call this Einstein because it's based on elbow in Stein, which is a mode of inference where we can optimize elbow within a force field defined by the Stein method on a set of particles. And what we've done is we've integrated all of the latest developments in optimizing this inference into a common framework, which was not available prior. And this framework is based on both very efficient computation of automatic differentiation using this module called JAX, and then a Bayesian layer coming from NumPyro, allowing us to use probabilistic programming techniques to express and verify our models and to run our algorithms, our inference algorithms. So Einstein combines three attractive properties. In particular, the Stein-based methods are non-parametric distributions and so highly flexible and can get us the correlation between parameters. Then we can express a large class of variational distributions because it's a hierarchical model. And finally, we get the scalability of variational inference. So by mini batch training, so we can compute our inference, our variational distribution on very tall, potentially tall data, though we're still limited in the number of parameters that we can have for our variational distribution. It's a little bit slow to change, sorry. So all of this is based on gradient descent-like framing of the Stein discrepancy. And while I will not go into any detail about the Stein discrepancy, I'll just give you some intuition about the gradient descent based method. So we have a number of particles which we want to approximate our posterior with here. And so we, through some introducing a kernel space, a kernel to smooth out the log, the gradient on the log posterior, we're able to compute a force field on these particles. This force field is additive, so this, the first component is an attractive force, which is seen by us taking the gradient on the log posterior and then smooth out by the choice of kernel. And there's been a lot of development in what sort of kernels can be used, but the original word used a radial Bayesian function kernel with a bandwidth computed by the log of the number of particles times the median of the Euclidean distance. And secondly, we have a repulsive force. So if we only had the attractive, they would all collapse to potentially one or several modes. But the repulsive force, which is the gradient on the kernel, means that that two particles are not able to get too close together, which means we're able to capture the posterior using our distribution. Using our set of particles. So, so we can extend this to a hierarchical model by replacing the log posterior by essentially an elbow term, and this is the gradient on the joint probability of our latent representation of our data, and then introducing a hyperprior over our latent parameterization, which is going to be a mixture of over Stein parameters. So this is the set of Stein parameters, and so we have a mixture model as a hierarchical model. There's a couple of practical considerations here. We use reparameterization, which is built into NumPyro, and the reparameterization trick has some problem, maybe problematic with certain types of distributions, like the von Mises, for example. So there's work to be done here to extend the type of implementation they have reparameterization, and then we have to support multiple particles, and in NumPyro we have this idea of a guide, which is automatically builds up a variational distribution over your particular model. And so we have to reinitialize this guide multiple times because we don't want every particle to be on the same spot at the same point in space. And finally, it's compositional. So here it's shown with the using elbow, but we could also introduce other more general loss functions in substituting into our attractive force here. So we now have a hierarchical model based on this on Stein, and a final major component is non-linearity. So for our repulsive force, we introduce a scalar we multiply by a scalar for repulsive force, and what this allows is that for if we have a multimodal distribution, we can scale down the repulsive force and be able to better capture if we have this expectation, because points are allowed to go closer. Another thing is that if you have like if you have very tall data, your likelihood will dominate your repulsive force, and so scaling this up by the size of the data allows you to not have again mode collapsing. And finally, there's an implementation thing, which is when in theory we're working with the expectation over the distribution of our data, whereas in NumPyro, when we take the joint likelihood, whereas in NumPyro, well, we capture our data as one of the parameters, and so we essentially missing a factor n, the size of the data, on our hybrid prior. And the way we get around this is we ad hoc rescale our prior by the size of the data. This is just done directly in the inference algorithm. So so these are the major contributions to sort of Stein method as an inference algorithm. We then have introduced parameterization transforms. This is work done by all of the previous work I've shown is other authors who've shown these techniques, and what we've done is gathered them together in a single interface. But we've then introduced parameter transforms of the Stein force field of the particles to have to improve the loss geometry, which gives us better inference. So this is very much a practical aspect or application aspect of actually learning a particular posterior. And what this is we'd have a bijection, some transform on our parameters to a space with a simple geometry, and then we're able to transform the Stein force by this transform. What you can see here is we have a set of target distributions, and then we well, this is not us, but we're taking applying a neural network-based transform. We can compose this function k2, 8, or 32 times shown here to take the standard Gaussian and then transform it into these to these target distributions. And so we can do our inference on the Gaussian, and then an approximate, something close to the Gaussian, and then map the force into our target. Well, in this case, it would be the guide. And NumPyro comes included with this inverse autoregressive flow directly, which is worked by Klingma. Okay. Oh. There we go. And so why choose implement it into NumPyro? There's a number of different modules for this. Thomas mentioned Pyro, which is based on PyTorch, and there's also TensorFlow probability which is based on TensorFlow from Google. But the newest development in auto differentiation, also in compilation, is this module called JAX, and NumPyro is Pyro rebuilt with a JAX backend. And so just like Pyro, in NumPyro, we have a high-level interface for specifying probabilistic programs, which are just our models written up as a stochastic program. So in this case, it would just be a Python, simple Python function, but with these stochastic primitives like sampling from a normal distribution, sampling from Mises distribution. NumPyro comes with JAX, which is has auto differentiation as well as a lot of standard linear algebra implementations built and optimized into it. We have some problems with it, which is why we are probably going to switch this out with FoodHuck in the future, which is an implementation that's developed here at the computer science department at Copenhagen University, which gives us more control over exactly what is being parallelized as for example. But the JAX also comes with the molecular dynamics package and many other attractive things. Finally, we have automatic, in NumPyro, we have automatic modernization of discrete variables, which is what we want to learn hidden Markov models, like the one Thomas showed you earlier. Well, this is taken care of by simply putting in an extra parameter in our model and then done in the backend. So we want to take this implementation and use it for protein folding, which is the work that I'm doing together with Thomas Hammerich and Christoph Lai. So this is a previous approach to this, which is taking using Langevin dynamics to take a very crude representation of a protein and then applying the dynamics to get a final structure for essentially folding the protein down, and then imputing all of the missing atoms to get a final three-dimensional structure as well, and also some with correct global secondary tertiary structure, hopefully. So and we want to extend this to not just get a distribution over the final coordinates, but also get a distribution over our over the force fields. Yeah, maybe my colleagues might be joining now. Sorry about that. So where to take this to next is one of the problems is if we have, when we initialize, we have points that land too close to each other. So a simple solution to this, which is probably what we'll do first, is randomly restart the particles when we initialize them. Another way to approach this is this work by Shen et al., which is using Stein points. And here we are introducing particles one at a time. And they introduce two methods. One is a greedy method, where we have Stein discrepancy defined over our distribution. And then we try to put in a point which minimizes this discrepancy for each point. So it's very efficient for a low number of for when you have few particles. And the second method introduces this based on the herding algorithm. And so instead of taking the computing discrepancy with respect to keeping all of the points constant, they compute it as a convex Hall over the set of points and derive an algorithm from there, which allows you to put in your points. And just for reference, the SVG, which we talked about earlier, we have, so here they have just put the points in a lattice, and they then sort of, by this force field, get forced over the target posterior. And Monte Carlo, of course, will try to walk the particular underlying posterior distribution by using a Monte Carlo chain. Yes, so this is the work I've been doing with Ahmed Salim and Thomas Hammerich and Christoph Lai. If you have questions regarding the implementation, please let me know.
Okay, thanks a lot. I'm gonna knock here again. And so, you're welcome to ask questions about this work. Anybody?
Just a minor comment to add something. Some of the work reminds me to something in kernel smoothing, which is the kernel mean shift algorithm. I just wanted to throw that to my attention, to your attention, because for that there have been proposals in how to select the bandwidth, and it's actually usually you have to select the bandwidth in such a way that it is optimal for estimating the derivatives, because you want to follow like the flow of the you want to follow the gradient to reach to the mode. Basically, it's a different setting. I'm not so sure how it does it compared to yours, because for me this is quite new. But I just wanted to say that for that setting there exist bandwidth selectors that are selected according to the objective of estimating the density, the derivative of the density, and those bandwidths are typically smoother than the ones that you employ for estimating the density. It's just a comment that maybe is useful.
That's a very interesting approach. So a lot of the ongoing work has been in determining what sort of kernel you can use, and there's currently like 12 different. But it's interesting to explore whether choosing the bandwidth, in particular for the rate of basis function, whether we can exploit that as well to get better inference.
Yeah, I recommend you to check the book by Jose Enrique Chacon, Multivariate Kernel Smoothing Methods and Applications in Chapman Hall. It has a chapter devoted to that. Again, maybe it is helpful, maybe it is not.
Thank you.
Great to see helpful comments here. Anyone else? No one? Well, I at least know I've learned something, and that's really I should take a look at NumPyro and stuff like that, because there really seem to be quite some good results. Oh, here we're seeing the book that you recommended. He's got it lying around there. I hope you can find it in your library somewhere. If there are no further questions, if anybody still has one, please speak up. If not, then thanks again for your good talk, and we're going to move